So after learning the phasor diagram and equivalent circuit, next thing is to find out the losses. So to find out the losses, we'll have to use two types of test. One is called open circuit test. Another one is called short circuit test. So open circuit and short circuit test has similarity between them. So this one is short circuit test. Okay. So as we have learned the equivalent diagram of the transformer, so here you can see this R naught and X naught or RC and XM. These two components are called as no load loss component. These two can be found from open circuit test, and this X1 and R1. These two are winding resistance and reactance component. These two are can be found from short circuit test. So in open circuit test, some things are to be remembered is that we'll try to always connect with low voltage side and we'll keep the high voltage side open. So the logic behind keeping low voltage side to the supply and high voltage side keeping open is that, say, this supply, generally we have low voltage supplies are say economical. That means suppose we have a two transformer, one is of 400 volt and the secondary side is suppose 1600 volt. So out of 400 and 1600, 400 is easily available and or it will be less costly. And here what we'll do is we'll connect the transformer 400 side to supply and keep the 1600 side open. So this is what open circuit test. In case of short circuit test, what we'll have is that we'll reverse that. Here we'll connect the high voltage side to supply and low voltage side is will connect to a short circuit connection. And here you can see instead of open circuit we are connecting a voltmeter. So voltmeter has say high resistance, so it will practically give us a open circuit connection. And in case of short circuit we'll connect the emitter will have a very less amount of resistance, so it will practically it will work as a short circuit. So this is what the basics of open circuit and short circuit. So coming to the circuit diagram of these two tests, we'll have a voltmeter in parallel to the supply and emitter in series and a wattmeter connected to calculate the losses. So in the laboratory you will get open circuit and short circuit test for the transformer. So what we'll do, we'll connect the supply and we'll energize the transformer to up to its rated value. Okay, so rated value of voltage. Okay, and at this condition there will not be any load connected, so this emitter will give us a very small amount of current. That current is also called as a no load component of current, and wattmeter give us some amount of say wattage. So here there is no work done and the circuit is open, so whatever the transformer is taking from the supply will dissipate as loss. Okay, and we can call this loss as no load loss, and this no load loss is a component of hysteresis and eddy current loss. Next is short circuit test. So at this condition what we'll do, we'll create a short circuit path. Okay, so when we create a short circuit path, the supply we are providing to the transformer, it will be 10 or 20% of the rated supply, but the current that flowing in this condition will be equivalent to, or we have to flow the current that should be equal to the rated value of the current. Okay, so suppose we are performing this test and based on the MVA rating or KVA rating of the transformer divided by the voltage value, we'll get a rated value of current. So suppose we have a 1000 volt ampere or 1 kVA transformer we are using, and this side has voltage value of 500. That means the rated current at this side will be say 1000 by 500, that should be 2 ampere. So this should be low voltage side, so whatever the value is, so it should be equal to, or we have to energize this supply until this side or this emitter gets the rated value, and we have to calculate the rated value based on the transformer voltage, okay, on that particular side. So at the rated value of current, we'll say what we'll do is, at the rated value of current, we'll perform this test. Okay, so at this test, as the transformer will energize up to 10 or 20% of the rated value, will not get the effect from magnetizing component. So here the transformer winding will see a full load condition. That means the winding will have maximum amount of current, and the losses at that point will be considered as winding loss or called as copper loss. Okay, at the short circuit condition, if the test is performed at short circuit or rated condition, then this winding will also can be called as this full load copper loss. So from this test, what we can get is copper loss, winding loss, or full load copper loss. Okay, if the transformer is rated, say this test is performed at rated condition, then what we will get is full load copper loss. Now, say the losses are core loss and ohmic loss or copper loss. Okay, or it can be called as iron loss and copper loss. Okay, and core loss or iron loss is say that comes with eddy current loss and addition of hysteresis loss. Okay, so there are some other losses, stray load loss. Okay, so that will be due to leakage flux. That means that sometimes the transformer flux link with other components of or other parts of the transformer, so that will be called as stray load loss. Another loss can be in the insulation. Okay, so that can be dielectric loss. Okay, so now coming to this P core loss. Okay, the core loss is now directly proportional to this part of core loss is called hysteresis loss, and another part is called eddy current loss. So this is hysteresis loss is directly proportional to frequency, and eddy current loss is directly proportional to square of the frequency. Next, why transformer is rated in kVA? So kVA means kilovolt ampere or volt ampere. So the basic reason is that core losses depends on current. Okay, core losses depends on current, and this voltage is depends on iron loss. So the transformer has to be defined in kVA rating. Okay, so instead of kVA, this kilowatt rating, it has a term called VI cos phi. Okay, sorry for this bad representation. So VI cos phi, that means it has to be for a definite load. So but the transformer is now available for say all the range of loads, so it's rated in kVA. Now another important thing is efficiency. Now efficiency, we know it is output by input, or this input we can write as output plus losses. Also in case of say output by input, output can be written as input minus losses. So from that we can get this type of expression. Now in case of transformer, this efficiency we can write as output by output plus these two losses are available. So P core, and this is X square PCUFL. So this PCUFL is called as full load copper loss, and here the current at full load will have some particular current, say IFL, and the copper losses depends on square of the current and some particular other load X. Okay, so here X is some particular other load X which is not full load, or I can write I by IFL is equal to that particular loading X. So at some other load which is not full load, that will be some fraction, say at half load, the peak CUFL will be 1 by 4 times of full load copper loss. Sorry, the copper loss will be equal to 1 by 4 times of PCUFL. Okay, so based on this, we'll have the efficiency formula. So this is what I am saying is the basic idea about the efficiency. So in any book, we will get the say exact efficiency formula, and I will also try to bring that particular formula into that slide and say re-upload this again. Next, this all the efficiency is not that important, only that is important for say practical purposes. Now next thing is say voltage regulation. So at no load, the transformer will give us some particular voltage, say 230. Okay, so this is just an example 230. Now once we are adding the loads, what we will see, this voltage is getting lesser. Okay, and this is the minus of this 230 minus 212 by 230 will give us a percentage, and or some particular value that will be called as regulation. Okay, so this phenomena we can understand in case of say summer days, say at the evening time when most of the loads are connected to the transformer. We can see the speed of fan and the power of light, illumination of the light can be lessened. Okay, now next is polarity test. Here we can see the same polarity. If we connect two transformer into same polarity, this value of voltage will give us 0. And if we connect two different polarity, it will give us addition of that to quantity. So we have another important topic of transformer, which is called as auto transformer. So what will have a step up and step down auto transformer. So in case of auto transformer, what happens is that we see two different type of current entering into this winding, and here there is a connection in between two winding of the transformer. In case of normal transformer, there is the power will be transmitted through induction only, and in case of auto transformer, power will connect from induction and conduction. Okay, so we need detailed explanation of auto transformer that will say we'll do in a later time. Okay, next another important test is called Sumner test or back-to-back test. So here if you see, these connections are similar to what we have done in case of open circuit and short circuit test. So what we will do, there will be two set of transformer. So primaries of two transformer set will be connected to this side, and secondaries of this two transformer set will be connected to this side. So here what we are doing, instead of doing this test in one transformer, we are taking two transformer. So from this two transformer we'll have two sets of primary and two sets of secondary. So basically in the simple way, in the Sumner test or back-to-back test, primaries are connected to this side, which will be performed a no load test. Secondaries of this transformer will be connected to another supply, though those will say continue performing a short circuit test. So open circuit test in the primaries, short circuit test in the secondaries. So here the first condition is that the two transformers should be identical, so that the losses that registers in these two wattmeter which can be divided and can get for one particular transformer. So here in the result of Sumner test, what we'll get W1 as the core loss, that will be core loss of these two transformer. So this value, if we divide it by 2, then we'll get the individual core losses. Here W2 will give us the iron loss of these two transformer, and this value will be identical, so we'll divide it by 2. So W2 by 2 will be say copper loss of one particular transformer. So here what happens is that the test is performed as rated voltage as well as rated current. So the transformer will be energized to highest temperature, or say it will be energized to a say ideal condition, or sorry, the rated condition, most rated condition, or the full load condition. So at this stage the result will be more accurate and we can get some more information about the heat. Okay, so as we know the information about heat or heat rises in the transformer winding, so we can design proper insulation for the transformer. And instead of doing it in an actual full load condition, we are doing Sumner test, and that will result us saving in say energy. That means here we are providing a short circuit type condition, here providing open circuit type condition, but actually there is no work is done. The supply is only taking the losses. This supply is providing for core losses, this supply is providing for copper losses. So instead of doing a practical full load condition, we are doing this Sumner test, so which are say helping in saving energy for this back-to-back test. Okay, so this is the basic idea of using open circuit, short circuit and Sumner test instead of doing it in actual full load condition, is that to save the energy. Okay, so I think we have concluded the basic fast revision of the transformer. So what we'll do is we'll try to create more videos about another machines also in later time.